Okay, so we already discussed, the how we are going to find, the H for conduction problems. So basically, we are going to do a dimensional analysis. That means there is a dimensionless number, Lucent number, that will represent H. And when there's a convection, there are two things affect the convection heat transfer. One is fluid motion. So how fast this fluid flows. The other one is the fluid properties. Like, what is the how much heat transfer from water, how much heat transfer from air. There's to be difference because of the thermodynamic properties. So we are going to use one dimensionless number that represents fluid motion, which is Reynolds number, and the other dimensionless number that represents fluid properties, how fast this fluid can transfer heat. That is Prandtl number. So Nusselt number correlation has a form of, is actually a function of Reynolds number and Prandtl number. So basically, the general form is going to be some coefficient C times Reynolds number to the power n times Prandtl number to the power n. So finding the appropriate Nusselt number correlation for the given convection problem is what we are going to learn. So the same goes to chapter 7 for external forced convection, and chapter 8 for internal forced convection, and chapter 9 natural convection. Okay, so there's not much difference between chapters. So we are going to study all of them together. It's going to be very quick and very simple. Yeah. The final exam is also very quick and simple. You can do so. So if you want to decide that, I want to have a take-home exam. So let's assume that from today to the exam date, you have about 5 days. So assuming that you can study 8 hours per day, 8 times 5, 40 hours times, the 15 minutes per problem. So 160 problems I can give it to you. I was kidding. I'm just saying that, I want to, make this, each exam has the same weight. So I want to stick to the same rule. 4 problems for 1 hour. That's my guess. It's very subjective, isn't it? So let's talk about this Nusselt number correlation for external forced convection. External forced convection means you have a surface and there's a fluid flow on top of it. So when we have a fluid flow on top of a surface, there are two things that we studied in fluid mechanics. One can be laminar flow and the other can be turbulent flow. Of course, the heat transfer in laminar flow and heat transfer in turbulent flow should be different, right? So there's Nusselt number correlation for laminar flow. There's a Nusselt number correlation for turbulent flow. So there are several Nusselt number correlations. So to select right Nusselt number, you need to be able to determine whether it is laminar or turbulent. How can we do that? We can use Reynolds number. If the Reynolds number is less than critical Reynolds number, then it is laminar flow. If the Reynolds number is greater than the critical Reynolds number, then it's a turbulent flow. So whenever you have an external forced flow, you need to determine whether it is laminar or turbulent first, okay? Then what is the critical Reynolds number? It depends on the geometry. So for external forced convection over a flat plate, critical Reynolds number is 500,000. Then how do you determine this Reynolds number? By using this equation. Density times velocity, but this velocity is the uniform velocity outside of the boundary layer. So I'm going to put this subscript to show that this is the velocity, not inside the boundary layer, outside uniform velocity, times characteristic length. When you have a fluid flow over a flat plate, this characteristic length is going to be the length of the plate, okay? Not the width, the length. Of course, this characteristic length changes depending on the geometry. So there is a characteristic length for cylinder, there is a characteristic length for sphere, there is a characteristic length for non-circular things, so you need to make sure that you are going to use the right equation to determine this characteristic length, which is the same for the chapter 5. When you determine beyond number, there are different ways to determine the characteristic length, like a half of the thickness or volume over the surface area. Divide by dynamic viscosity. If you don't want to use dynamic viscosity, you can also use kinematic viscosity, which is velocity times characteristic length over kinematic viscosity nu. This is mu, this is nu. They are Greek letters. Anybody speaks Greek? No? So possibly mu or nu, I don't know how to spell them. So that's not V for sure. That's a new Greek letter. That's because mu, dynamic viscosity, is density times kinematic viscosity. Then you may have one question. Oh, we already have a viscosity. Then why do we need to have another viscosity? That's a good question. The unit of this kinematic viscosity is meter square per second. And there is another, the property that shows how fast something goes. This one shows how fast fluid moves, right? And there is another parameter that shows how fast it moves. What is that? Thermal diffusivity. Then what is the unit of thermal diffusivity? Meter square per second. So if you use a kinematic viscosity, you can use dimensional homogeneity by comparing these two. Then what is the dimensionless number comparing these two? Prandtl number. So this Prandtl number is mu over alpha. Just for your information. So the viscosity was developed. The dynamic viscosity was developed first, and we learned that if we divide by density, we get kinematic viscosity that has the same unit as the thermal diffusivity. So that's how we found Prandtl number. So the first, the thing that you need to do is to check whether it is laminar flow or turbulent flow. Then there are a set of Nusselt number correlations for laminar flow. There are a set of Nusselt number correlation for turbulent flow. And that's it. There's one more check that you need to do. One is heat transfer boundary condition. So heat transfer boundary condition can be constant surface temperature or constant surface heat flux. So the second thing that you need to check, the first one is Reynolds number to determine laminar or turbulent. And the second thing is heat transfer boundary condition, whether it is constant surface heat flux or constant surface temperature. So once you find the combination, so let's say laminar constant surface heat flux, there's a Nusselt number correlation. Laminar constant surface temperature, there's a Nusselt number correlation. Or turbulent constant surface heat flux, there's a Nusselt number correlation. Turbulent constant surface temperature, there's a Nusselt number correlation. In the final exam, I'm going to provide every Nusselt number correlation we are going to use in chapter 7, 8, and 9. So by calculating Reynolds number and by determining the fluid flow and also heat transfer boundary condition, you are going to find, okay, I'm going to use this Nusselt number correlation and then use that to determine H. Okay, that's it. Chapter 7, fluid flow over flat plate. Then there are a few extra that we need to know, a few details. The first one is We know how to determine Reynolds number, right? What about this Knudsen number? How do you determine that? This Knudsen number can be determined by H, L of C over K. So once you get Knudsen number, you already know the characteristic length from here. And thermal conductivity, you can find it from a property table. I'm going to provide it in the final exam, so you don't have to find it. Then you get H right away. Okay? So this is a procedure. When you determine that, oh, I have a fluid flow, I have a convection heat transfer, and the fluid flows over a flat plate, then you can say, oh, this is the external forced convection. So I'm going to determine whether it is laminar or turbulent. Then I'm going to check whether it is constant surface temperature or constant surface heat flux. Then there is a Knudsen number correlation for that combination. Then just use that one, and you will determine Reynolds number and Prandtl number. That will give you Knudsen number. Once you get Knudsen number, you can find H. Okay? Any question? You should have one question if you studied chapter 5. Yes. Yes. What is the Biot number? Biot number is H, L of C over K. In the last 5 years, I taught this class. You're the first one finding this one. So, I'm sorry, I can't. I have to say that. Oh, there's externality. Then you find the answer. Then it cannot go backward. I just want to make sure that everyone is happy, right? So, they look the same, but they are not. Why is that? What is the focus of this Biot number? How heat transfer within a solid, right? So what is the thermal conductivity? Is it the thermal conductivity of solid or the thermal conductivity of liquid? This should be the thermal conductivity of solid. Then, for this Knudsen number, what do we study? How heat transfer within the fluid. So what is the thermal conductivity? Whose thermal conductivity is this? Surface? No, fluid. So this K should be the fluid thermal conductivity. So the Biot number, Knudsen number look the same, but they are not, because one, we use a thermal conductivity of fluid because we are focusing on the convection. And the other, it's the thermal conductivity of solid because we are focusing on transient conduction in the solid. Okay? Any question? Before we actually go, to find some Knudsen numbers. Not yet. There's to be one more question. One more thing before we go over. I want to make, the very nice one-page slide. So you can copy and paste. No, you can. Yeah. What? Oh, so C and M and N are available from the Knudsen number correlation. So we will see in the next 2 minutes, okay? There's one more thing that you need to study. It says that when the Reynolds number is greater than 500,000, it's a turbulent flow. Less than 500,000, it's a laminar flow. What does it mean? In general, in reality, what happens is that, initially it's a laminar flow and it becomes turbulent flow. So this is the location when Reynolds number hits 500,000. Then the question is, what about if the Reynolds number is about 700,000 or 1 million? Then do we have to say it's a completely turbulent? Not necessarily. Initially, it was a laminar and it becomes turbulent. So unless a fluid flow starts with the turbulent flow from the beginning, it's going to be laminar and turbulent mixed, right? So when we check Reynolds number, there are 3 different fluid flow. One is laminar flow when Reynolds number is less than this one. The other one is not turbulent but mixed flow. So initially turbulent, initially laminar, and it becomes turbulent after it passes when Reynolds number is 500,000, because it depends on the length of the plate, and there could be some exceptions, some special cases when turbulent flow, to start from the beginning. What is that? When we have a tripping device at the beginning, like any obstacle that interfere fluid flow, then laminar flow cannot start, turbulent flow starts. There is, the one thing that is famous using this phenomenon. What is that? What is the sport? The different angle. Yeah. So do you remember the shape? And have you seen the surface of this ball? Is it smooth? Not really. It's not smooth. Why is that? Because those are the tripping devices. Those holes, the rough surface will introduce this turbulent flow earlier, so it can reduce the pressure drop. So the golf ball can fly further, because it's going to minimize the pressure drop between the front and the last. So if you make the golf ball smooth, and then when you hit it, it won't fly that far, because the pressure drop is going to be significant when there's a laminar flow starts and become turbulent. So what happens is that it's actually fluid mechanics, but it's going to be fun. So what happens is that when you have a laminar flow and it becomes turbulent, this is what happens. So we have a significant, the high pressure here and low pressure here. But if you make this surface rough and turbulent flow starts earlier, so what happens is that, and there's a fluid flow goes, oh, this is rough, so let's introduce turbulent flow as soon as possible, then it goes like that. So the pressure drop is not as significant, maybe this small. So the pressure difference between these two is way less than this one, so it can go further. Yes.
Like on like bar.
Yes, that's why when you jump into an airplane, look at the wing, they don't look smooth. There are lots of the lines and bolts. They just leave them as is, because you want to introduce turbulent flow as early as possible. Then one more question. This is supposed to be, you are supposed to study down in fluid mechanics. So one more thing. What about table tennis? The size of the ball looks similar to the golf ball, right? But they look smoother. Then what about if you make it rough, like a golf ball? Do they run faster? Not necessarily. The Reynolds number is a function of velocity too. So unless you can hit table tennis ball by this flap, it won't go to turbulent flow. So no matter what, it's a rough surface or smooth surface, is going to be still laminar flow. So making rough is going to go against, because it never, end up in turbulent flow. So two different things. Anyway, that's a fluid mechanics. You don't have to know that in this course, right? But it's good to know, right? So this one-page summary shows everything that you need to know in chapter 7. Any question? Let me add one more. There's one exception. There's a Nuisance number correlation is for fluid flow over a cylinder. So there's a Nuisance number correlation only for fluid flow over a sphere, over a cylinder. That Nuisance number correlation is going to be, we are going to study that one too. So there are two different external fluid flow, external forced convection One is flat plate, the other one is cross flow over cylinder. So that is everything. Then let's study, yeah. What table number?
Table number is for the eminent.
There's no table. I will provide them.
Like the homework.
Yeah, you can, check the PowerPoint slide. So the first one is lamina and constant surface temperature boundary condition. I told you that there will be 3 fluids and there are 2 heat transfer boundary condition. So each combination you have a Lucent number. So let's learn the easiest one, lamina and constant surface temperature. That is shown here. Lamina and constant surface temperature, which is isothermal temperature. Then what is the Lucent number? This one here, Lucent number correlation is going to be 0.332 Reynolds number. You know how to determine Reynolds number, to the power 1/2. And Prandtl number, that's a material property. You can find it from a table to the power 1/3. Excuse me. So that's how you determine Lucent number. It's super easy, isn't it? Or is it difficult? Or super difficult? I don't believe you. We will solve a few problems together and you will know how easy these are. Then let me show you another slide. So this one is lamina isothermal plate, lamina constant surface temperature. Then what comes next? Oh wait, lamina isothermal plate, and we have a Lucent number correlation. So let's compare this Lucent number correlation with this Lucent number correlation. Look at the numbers, 0.332. Reynolds number to the power 1/2. Prandtl number to the power 1/3. This Lucent number, 0.664. Reynolds number to the power 1/2. Prandtl number to the power 1/3. What is the difference between these two? This one says local. This one says average. What does it mean? What does it mean? It means when you have fluid flow, there's a boundary layer. Heat transfer by convection in this thin boundary layer and heat transfer in this thick boundary layer. Do you think, are they the same? No, they're not. So H value here and H value here, they are not the same. Then what do you want to do? There are one way you can do. You can make it a number of steps and calculate H for each of them. H1, H2, H3, H4, H5, H6, and H2 million. And then calculate the sum of them. That's one way you can do. If you want to do this way, local boundary layer property. Oh, I don't want to do that. But I'm an engineer. I like simplification. I'm going to make an average. So can I get average value? Yes. That average value is average boundary layer parameters. So there are 2 Lucent number correlations. One for local Lucent number. And you don't have to use that in undergraduate heat transfer. Average Lucent number is okay. All right? Average Lucent number, you see a bar on top of it. This shows that this is the average. Average Lucent number correlation is 0.664 Reynolds number times Prandtl number. So whenever you have a fluid flow, over a flat plate, and you calculate Reynolds number and determine that that's a laminar flow. When you check the heat transfer boundary condition, that's a constant surface temperature boundary condition. This is the Nusselt number you are going to use. That's all. Any question? It's very surprising. It's too easy, isn't it? No? Then there's one thing that you are, that you may be interested, which is that, oh, we are here to study this Nusselt number. What is this C? It's always, the beneficial to study fluid mechanics and convection heat transfer together because there are lots of similarities. So this is just for your information. If you want to determine friction coefficient, it's going to be 1.328 divided by square root of Reynolds number. Then you may have a question. What is friction coefficient? You're supposed to study that in fluid mechanics, but let me briefly show you. The friction coefficient means, let's assume that this is a Chippewa River. This is Chippewa River. This is Island Park. And there's a Chippewa River. Have you been there? So let's jump in. I'm standing right here. So there's a rapid flow. So what do you feel when you stand in the middle of Chippewa River? You'll be okay? Not much. You get some pressure, right? You get some force. That is called drag force. Water is pushing you because it is flowing. Then there is a force associated with that. If you want to calculate that force, we use friction coefficient. There are two drag force. One is pressure drag, which means when fluid flow is this way, there is a high pressure that is called stagnation pressure. There's a low pressure. So the force due to the pressure difference, high force, high pressure minus low pressure times the cross-sectional area, that is called pressure drag. So the force associated with pressure from the front and low pressure in the back, that is called pressure drag. There's one more drag, is friction drag. So there's a boundary layer developed on top of this, the hair. So this is head, and there's a boundary layer developed. This boundary layer is going to push you backward because there's a friction, right? That's called friction drag. Then how do you determine this friction drag? So this is pressure drag, and this is friction drag. How do you calculate that? We are going to use friction coefficient, which is this one, multiplied by 1/2 times velocity square times area density. That's how you determine drag force. So when there's a fluid flow, you always calculate two things, pressure drag and friction drag. So pressure drag can be determined by this equation. Friction drag can be determined by that equation. So that's how you determine drag force. When you go to thermal lab for EGR456, there's a wind tunnel, right? The one that you measure is going to be the combination of these two. Of course, one can be significant and the other maybe not. How do we know that? When the fluid flow is this way and your object is standing this way, then the friction drag is going to be minimum. Pressure drag dominates the drag force, then you can neglect friction drag. On the other hand, when there's a fluid flow and your object is going to look like that, then the significant drag force is going to be friction drag. Then in that case, you can neglect pressure drag. When you design an airplane, the wing is more like this. So friction drag can be very important. What about this fluid flow over a flat plate. Friction drag dominates that. Therefore, you may want to study friction coefficient too. That's why I provided friction drag and loose end number on the same page. You will see this combination in the next slide and so on in chapter 7. So that's everything about the theory. Let's go find other loose end number correlations. So this page shows loose end number correlation for laminar constant surface temperature, turbulent constant surface temperature here, average boundary parameter, friction coefficient for turbulent flow, loose end number correlation for turbulent flow. By the way, this slide is going to be provided in the final exam. Then the next one is going to be mixed boundary condition. There is friction coefficient for mixed boundary condition. There's a loose end number correlation for mixed boundary condition. It looks complicated, but it is not. So A, the coefficient is 871. So this one is 871. And this one is 871. Okay. So when you calculate Reynolds number for fluid flow over a surface over a flat plate, and the Reynolds number is greater than the critical Reynolds number, your assumption is going to be, oh, it's a mixed boundary condition. Then when can we use turbulent boundary condition? If there is any tripping device on the surface, let's say that there is a small tripping device is interfering in the fluid flow, then you assume that after that it's going to be just turbulent flow and use this loose end number correlation. Without those tripping devices, use this mixed boundary condition. Okay? Any question, or is it too fast? Yeah. Yeah. This one is mixed isothermal. And there's information about the tripped boundary layer. Boundary layer has been tripped and turbulent flow starts at the beginning. Then the loose end number correlation is going to be this one. So these three loose end number correlations are for constant surface temperature. What about constant surface heat flux? There is unheated starting length, but don't worry about that. That's a very unique case. So we are going to focus on uniform surface heat flux boundary condition. Then if you have a uniform surface heat flux boundary condition, what is the loose end number correlation? That loose end number correlation is given here. For laminar, this one. For turbulent, this one. There is no mixed, because there is no mixed boundary condition, loose end number correlation in the textbook. You can Google them, but it won't be in your final exam. So that's everything. Let's review what we need to do whenever we have a convection heat transfer problem. First, check whether it is external flow or internal flow. How do we check? When the boundary layer develops freely, then the external boundary condition. When the boundary layer meets together, that's going to be internal boundary condition, which is like fluid flow in a pipe or duct. So if it is internal flow, then we go to chapter 8. Since it is external flow, we stay in chapter 7. We haven't studied chapter 8 yet. We will do that. And then you decide whether it is over a flat plate or over a cylinder. Then if it is over a flat plate, then find the film temperature to determine density, thermal conductivity, viscosity, and etc., those properties. And we calculate Reynolds number to determine whether it is laminar, turbulent, or mixed. And then we determine a heat transfer boundary condition such as constant surface temperature, constant surface heat flux. Forget about unheated starting length because that's very unique. And we are going to focus on average parameters and then go select appropriate Lucent number correlation from the table that I'm going to provide. That's all. There's one more missing, which is, what about if it is a cylinder? What about if it is a fluid flow over a cylinder? Like, the duct or pipe outside of this building or inside this, behind this, the ceiling, there's a duct pipe or on the roof. Then how do we determine their heat transfer coefficient H? So there are some characteristics that you need to know in terms of fluid mechanics. I'm not going to discuss that because you are supposed to know that. But briefly, this is the reason why we want to make the surface rough when you play a golf. So you can minimize the wake area that will decrease the pressure in the back. So this is the smooth surface, this is the rough surface. So in that case, you have a less pressure drop. But anyway, that's not the important. The important thing is, what is the Lucent number correlation? That Lucent number correlation is available right here. So whenever you have a fluid flow over a cylinder, this is the only Lucent number correlation that you are going to use as a function of Reynolds number and Prandtl number. The equation looks pretty ugly, but it's a function of Reynolds number and Prandtl number. Don't make a mistake when you solve that equation. Cylinders of non-circular cross section, you don't need to worry about that. This one is more like an internal fluid flow. So we are going to study that in chapter 8. Okay. Any question up to here? So we studied Lucent number correlation for fluid flow over a plate and fluid flow over a cylinder, this one. And that's all in chapter 7. These are just some, for your reference when you have a multiple arrays of, the cylinders, then the only difference is that how do we determine Reynolds number? So depending on how they are aligned, these are how we determine the maximum velocity. We use the maximum velocity to determine Reynolds number. Once we determine Reynolds number, there's a table to determine Lucent number, but it won't be in your final exam. Okay? That's it. Let's solve a problem together. A flat plate. So we have a flat plate, looks like this. And there's a fluid flow on across the top of the plate this way. And the temperature of this fluid flow is going to be 22 degrees Celsius. And the temperature of the plate is maintained at a temperature of 32 degrees Celsius. That shows the heat transfer boundary condition. So the surface has a uniform surface temperature. This is constant. And what is it? 32 degrees Celsius. So there's a heat transfer in this direction. So Q. So if you want to determine Q, what we need to know? H. How do we determine H? By Lucent number. So we are going to determine the average heat transfer coefficient, which means H. And we are going to determine the convection heat transfer rate, Q. And drag force. That's just for, as a surprise, fluid mechanics. Drag force. So let's do that. And the velocity of the fluid is 0.5 meter per second. U infinite is 0.5 meter per second. So what is the first step? You need to determine whether it is external flow or internal flow, of course. No one expects that this one is an internal flow. So chapter 8, we don't care about chapter 8. This is an external forced flow, so chapter 7. And when you determine that it's an external forced flow, then there are two things that you need to find. The first one is laminar, or mixed, or turbulent. That's the first thing. The second thing is heat transfer boundary condition. We already know this one. It's a constant surface temperature boundary condition. So the only thing that we need to know is laminar, mixed, or turbulent. How can you do that? You need to determine the Reynolds number. So let's determine Reynolds number. How do we do that? Reynolds number can be determined by density times velocity times characteristic length over dynamic viscosity. If you do not want to use dynamic viscosity, you can use kinematic viscosity nu velocity characteristic length. So where can we find them? I'm going to provide those thermodynamic properties in the final exam, so don't worry about that. So the velocity is 0.5, so this one is 0.5 meter per second, and the characteristic length is going to be the length of the plate, 0.2, not the width, okay? It's going to be in the same direction, the length of the plate. So this is 0.2 meters. What is the kinematic viscosity of water? The kinematic viscosity is 857.10 to negative 9 meters square per second. So if you do the calculation, Reynolds number is going to be 117 times 10 to 3. Is it laminar flow or turbulent flow? You need to compare this number with critical Reynolds number. What is the critical Reynolds number? 5 times 10 to the 5th, which is less than this one. So this is laminar flow. So let's find Dusel number correlations for laminar constant surface temperature. Where are you? Laminar constant surface temperature. It is here. Laminar constant surface temperature average friction coefficient is 1.328 square root of Reynolds number. Let me write this equation here. Average friction coefficient CF is going to be 1.328 divided by square root of Reynolds number, and average Dusel number is going to be here 0.664 Reynolds number to the power 1 over 2, Prandtl number to the power 1 over 3. So let's solve this Dusel number first. What is the Reynolds number? Here, 117 times 10 to the cube. And what is the Prandtl number? Prandtl number is going to be provided 5.83. Or if I give you kinematic viscosity and thermal diffusivity, you can also determine Prandtl number. So if you calculate that, you get Dusel number. And Dusel number is H of C over K. So what is K? Thermal conductivity of water is 0.613 watt per meter Kelvin. I will provide those property values. And the characteristic length is going to be the length of the plate, 0.2 meters. I'm sorry, 0.2 meters. So this one is 0.2 meters. So can we determine H? Yes. The H is going to be 1253 watt per meter square Kelvin. Is it difficult? Not much, right? Then how can you determine heat transfer? You can use thermal resistance network, delta T over R, Or you can just use Newton's law of cooling because they are the same. H times A times temperature difference, delta T. So what is H? Oh, H is here. What is the area? 1 meter times 0.2 meters, 0.2 square meter, temperature difference, 32 minus 22. Can you determine Q? Yes, you can. That Q is going to be 2.51 kilowatt. So if you calculate this one, Q is 2.51 kilowatt. Just for your information, let's determine the friction drag. So the drag coefficient can be found. We know the Reynolds number, 117 times 10 to cube. Then the friction coefficient can be found, which is 1.328. 1.328. Then you can use the drag coefficient equation. Oh, I need a space. Drag coefficient, F of D, can be found by friction coefficient. A drag force can be found by friction coefficient times density times velocity square times area divided by 2. We already know the friction coefficient here. Density of water is 1000 and the velocity is 0.5. Area is 0.2 square meter. So you have everything. Can you determine the drag force? Yes, you can. It is 0.097 Newton. So this is a very typical problem you can expect from this chapter. Can you solve it if I give you this one in the final exam? Yeah. Not very complicated, right? So it may take some time, but procedure is very straightforward. You determine whether it is external flow or internal flow. Once you determine that it's an external flow, you check the Reynolds number to determine laminar, mixed, or turbulent. And then check the heat transfer boundary condition. Then you get the Nussen number correlation. Just solve it to determine H. And once you determine H, use the heat transfer equation that you studied in chapter 3 or chapter 5, find and solve the heat transfer problem. That's what you will do in the final exam. So in the final exam, you will see 3 or 4 problems. You will use Nussen number correlation for each of the problem to determine H. And use that H to determine Q or T is going to be what you will do. Any question about this problem before we go to the next problem? Is it too fast or too slow? Not too slow. That means good. No? A little fast. Okay. For the lectures this week, I will post them on Blackboard as soon as possible so that you can, go review those lecture videos if you need any help. Or if you got stuck in solving a problem, just send me an email. Make a photocopy of your solution so I can look at that and then give you my, the feedback. Okay. If you have any, the problem solving homework problems or the PowerPoint problems, just, send me an email with a photocopy of your solution so I can review and then get back to you. But chapter 7, chapter 8, chapter 9, they look very similar. All you are going to do is to learn how to select the right Nussen number. That's it. So in this case, the selection process was simple. Laminar, turbulent, mixed, and constant surface temperature, constant surface heat flux. Find this combination, you get this Nussen number correlation. And you will see a list of Deussen number correlation, exactly the same as in the PowerPoint slide. So I will actually do photocopy of the PowerPoint slides and then combine them and then give it to you as a reference table in the final exam. Let's go to the next problem. We have a tube and there is a fluid flow over this tube. So there's a tube and there's a fluid flow over this tube. Then, is it an external forced convection or internal forced convection? It depends on the boundary layer. So boundary layer develops like this. So there's a boundary layer and there's an outside of boundary layer. So if you have outside of boundary layer, that means it's an external forced convection. When you have an external forced convection over a cylinder, there is only one Deussen number correlation. That is this one. Oh, this one. So this problem is actually very simple. You are going to determine Reynolds number and Prandtl number should be given and just solve this complicated Deussen number correlation. Once you get Deussen number, you are already halfway done. Find H and solve it. So let's do it together. Reynolds number first. How do we determine Reynolds number? Where are you? Reynolds number, right there. Reynolds number can be determined by this equation. Reynolds number is velocity times characteristic length over kinematic viscosity. And the velocity is given 3 meters per second. If you have a fluid flow over cylinder, this characteristic length is going to be always the diameter. So what is the diameter? 20 millimeters, 0.02 meter. What is the kinematic viscosity? I will provide that in the final exam. You are actually going to use a property table when you go to the field. And the kinematic viscosity is simple, 12.6 times 10 to minus 6 meters square per second. So you get Reynolds number. What is the Reynolds number? 5,714. And what is Prandtl number, by the way? Prandtl number is 0.717. So we have a Reynolds number and Prandtl number. Can you determine Deussen number? Yes. Of course, it's going to take time. I have the answer, so let me just give it to you. I don't have the answer. So Reynolds Deussen number is going to be some number, but I have H. Deussen number is going to be H times characteristic length over thermal conductivity. And characteristic length is going to be the diameter, 0.02 meter. And thermal conductivity is 0.0233 watt per meter Kelvin. And now I have this H. H from this equation is going to be 38.56 watt per meter square Kelvin. Then we are ready to solve this problem. So always all the problems in the final exam it's a two-step process. First, find H. And second step is going to be then solve the heat transfer. So what we need to determine? The rate of heat loss per unit mass of the water. What? Yeah, we can do that, but that's weird. So the rate of heat transfer, how can we determine that? So there's a thickness. I don't like this problem. So we have this tube, this much, and there's a water, air outside, minus 20 degrees Celsius. There's a water. We can assume that the inner surface temperature is close to the water because the heat transfer between the water and the surface is going to be very fast. So this is 0 degrees Celsius. How many resistances between these two? 1 and 2. So this one is natural log R. Can you see that? Natural log R2 over R1 over 2 pi KL. And this one is 1 over H times 2 pi R2 times L. So I'm going to assume that the length is going to be unit length, 1 meter, 1 meter. And what is the R2? Thickness is 2 millimeters. Radius is 10 millimeters. I'm sorry. So R2 is going to be radius 10 millimeters, thickness 2, so 12 millimeters, 0.012 meter. And H, we just found H, 38.56. 38.56 watt per meter square Kelvin. And thermal conductivity K is, this is copper, so should be very high, 401 watt per meter Kelvin. And R2 is 0.012. R1 is 0.01. And Q can be found, so this one is R1, this one is R2. Q is going to be delta T over R1 plus R2. We already have R1 and R2. What is delta T? 0 degrees Celsius minus 20 degrees Celsius. So can you determine Q? Yes. Q is going to be 58 watts. That's how you determine the rate of heat transfer. Now, if you want to determine the rate of heat loss per unit mass from the water, then how can you do that? You need to determine the mass of the water. So how do you determine the mass of the water? Mass of the water can be determined by density times volume. This volume is going to be pi R1 square over, it's not the diameter, times L times density. So density is 1000. R is going to be 0.01. Length is going to be 1 meter. So you can determine the mass of the water, which is 0.314 kilogram. So if you want to determine Q over Q per mass is going to be 58 watt divided by 0.314 kilogram. So that's how you determine Q. That one is a stupid problem, so I'm not going to provide such a problem in the final exam. Maybe up to here is okay. So that's everything for chapter 7. Any question? On Thursday, we are going to study internal forced convection and free convection. That seems a lot, but that's not, because all we are going to do is how to find Dussel number correlation. So I think we can finish less than an hour, then we can do a quick review for the final exam. Okay? Any question? If you have any question about your second exam grade, let me know.